Chapter 3, Exercise 7. Show that if R is a relation, then the field of R is equal to the union of R. Okay, first thing we should clarify is what exactly is the field of R. So, the field of R is going to be the domain of R unioned with the range of R. And we defined the domain of R and the range of R in the previous video, but just so you can recall, it's going to be a set of X in the union of R such that there exists some Y such that X comma Y is in R. And then the range of R is going to be Y in the union of R such that there exists some X such that X comma Y is in R. Very similar definitions. Note that X corresponds to the left of the ordered pair, Y corresponds to the right of the ordered pair. And the field is going to be whatever is inside either of these two. Okay, so let's do this, right? So first, we're going to show that the field of R is a subset of the union of R. So let's suppose X comma Y is in the field of R. Or rather, to make it a little more general, some element Z is in the field of R, right? Then we know, as we just defined, then Z is either in the domain of R. Oh yeah, that was wrong. That was completely wrong. Okay. Z is either in the domain of R or Z is in the range of R. Okay. So, if Z is in the domain of R, then Z satisfies Z is in the union of R, and there exists some Y such that Z comma Y is in R. And then otherwise, if Z is in the range of R, then there exists some X such that X comma Z is in R. And there you have it. So, or rather, just to keep the inferences uniform. Okay, so, yeah. Essentially, what I'm saying is that if Z is in the domain of R or Z is in the range of R, then automatically we know that Z is in the union of R, right? So this side of the inclusion is pretty straightforward. All right, if Z is in the domain of R and it's in the range of R, then both hold. So, regardless of the case, or rather, I feel that's an awkward sentence. In any case, Z is gonna be in the union of R. Okay? And this means that, let me add a new page before we run out of space. Okay, this means that the field of R is going to be a subset of the union of R. as we'd expected. And now what we're going to do is we're going to show that 2, the union of R, is a subset of the field of R. Okay, so now suppose that Z is in the union of R, right? Okay. This means that there exists some bigger Z in the union of R such that little z is in big Z, right? And then big Z being in the union of R means that there exists some x comma y, or rather let's call it little r, in big R, such that big Z is in little r. Okay. Right, this is kind of confusing, I know. But since not this R, big R is a relation, Z, or rather little r, is equal to x comma y for some x, y, or rather let's just leave it at that, for some x, y, and not say any more about that, right? Okay, so essentially what this means, and just like to skip ahead a little, this means that either z is equal to x or z is equal to y, in which case, or rather, if z is equal to x, then it's in the domain of R. If z is equal to y, then it's in the range of R. If it's equal to both, or if you pick a different R that z is a part of, then it's going to be in both. So either way, it's in the union, or it's in the field. Okay, right. So how do we keep on going now? So, oh my god. Whoops. So, if R is equal to x comma y, then now we're going to go back down. We kind of went up the chain of unions, now we're going to go back down the chain of unions. So if R is equal to x comma y, then big Z is in x comma y. And what this means is that Z is either equal to the set containing x, or Z is equal to the set containing x and y. Right? So, what does this tell us? So little z is in the set containing x, or little z is in the set containing x comma y. Okay. Now, if z is equal to x, then then z is in the domain of R, because x is in the domain of R. So if z is equal to x, then z is in the field of R. Okay, now if z is equal to y, then z is in the range of R, because y is in the range of R. Thus, if z is equal to y, then z is in the field of R. And then if z equals x equals y, then both cases apply. I mean, it can be pretty obvious. I don't know. I feel like math is strange in that way, where some steps can feel obvious to some people and completely like a very big jump in logic to others. So I just want to come back here and cover my tracks. And specifically, it's here. So this statement, right, I kind of just jumped all the way here, and I want to rectify that. So let me just move the rest of the proof down here and go back. So if Z is in the set containing X, then Z is equal to X, right? If Z is in the set containing X and Y, then Z is equal to X, then Z is equal to X or Z is equal to Y. Now, what does this mean? What am I trying to say? I'm just unpacking this or right here into the two cases that it envelops, right? And what I kind of just did in my head without realizing until now is that I just kind of jumped from this statement to not even this statement. So we have this case right here, we have this case right here, and I kind of combine them both into like either Z is equal to X or Z is equal to Y, which is a valid inference. I just feel like I should justify it a little more. Okay, so the only two possibilities for Z to be in X or Z to be in the set containing X and Y are that A, Z is equal to X, B, Z is equal to Y, or C, Z is equal to X, which is equal to Y. If you've done a lot of math before, you probably see this and roll your eyes a little. But I think sometimes being a little too strict is better than being a little too loose. Anywho, now going back to the proof after that brief aside. Okay, so we have that if Z is equal to X, then Z is in the field of R. If Z is equal to Y, then Z is in the field of R. And those are the only two cases we need to check. Because if Z is equal to X and X is equal to Y, then both cases apply. No matter what you do, Z has to be in the field of R. Thus, the union of R must be a subset of the field of R. And we conclude then that the field of R is the exact same set as the union of R. The union of R. Which is a nice fact. We can now think of the union of R and the field of R in terms of each other. Which I don't know when it comes useful, but it might, so it's good to have in mind. With that said, I hope this video was helpful, and I will see you in the next one. Bye-bye.